Hello everybody and welcome to the NPTEL online certification course on microelectronics devices and circuits. We start from where we left in the previous module. We had initially done the work on MOS differential amplifier, and we saw that the overall gain of an amplifier depends on the value of your transconductance of the driver transistor and the drain resistance. So, if we discuss the previous turn, what we saw was that if you wherever you are giving the input, please understand, wherever you are giving the input voltages, this is the input voltage, right, this one, these transistors are known as driver transistors, right. Further, if you remember, we had RD here, which is the drain resistance, right, RD. This is the RD value, but in reality when you do it on IC or on a chip, when you want to fabricate it, this resistances will be performed by MOS devices. Typically if you use a PMOS device here, you have a larger resistance being offered at this particular point. So, we will see as we move along how it works out, but typically you have learned two things, that the gain is given as GM times RD. Your CMRR is infinitely high because of the fact that your AD, it is basically defined as AD by AC, right. If you take in dB, then it will be 20 log of AD by AC, and this is equals to your CMRR, right, and this is typically very high quantity which you get, approximately 10 to the power 5 or 6. Ideally this should be infinitely large. What we will do today is we will actually look into MOS differential amplifier part 2, where we will be actually replacing those RD, the drain resistances, by the typical PMOS. So, before we go that, let me just do one more amplifier design, and that is known as MOS cascode design. Please understand, it is not cascade, it is cascode, right. So, you have a O here, cascode design, right, you have a MOS cascode design. So, let me draw for you how, so this is, but please understand, this is, we are slightly moving away from differential amplifiers. Differential amplifiers, you are feeding signals in a differential fashion to both the inputs of the gate. Here it is single stage amplifier, it is not a differential stage. So, but we will see what the advantage of it is as far as designing is concerned. So, we apply a voltage source, a current source here, and then this you have got a VDD, right, and then what we do is, this is quite interesting, that this is Q1, this is Q2, and this is plus minus V in. We apply the voltage here V in, and we apply a fixed bias here VB. This Q2 is known as the cascoded device, and this is your input device. You are feeding the input to this and you are taking the output from here, right. Now, you see this is, if you look very carefully, this Q1 is basically a common source design. So, this is a common source amplifier, whereas this one, if you look very carefully, is basically a common gate amplifier. So, when common source amplifier and common gate amplifier are stuck together or they are made together, then we define that to be as a cascoded amplifier, right. So, what is a cascoded amplifier? You have a common source amplifier, you have a common gate amplifier, and when they are when they are attached like this, such a manner that the source of one is connected to the drain of the common source, then we define that to be as a cascoded case. Now, if I try to plot the V out versus V in to get the transfer characteristics curve here, right, let us suppose this point is x, right, then if I, this is V out, then I get something like this. This is your VTH1, this is VDD, right, and this is VB minus, I will explain to you, VTH2. If you see, as my V in happens to be very low, right, when my V in is very low, I can safely say that my Q1 is cut off, right. So, I am just finding out the voltage at this particular point. then if this is cut off which is in the off state, if this is the V in is very low in the off state, then you automatically get what that this is for this is for V out here, and this is Vx. So, Vx is plotted in this manner and V out. So, let us look at V out first. When V in is very low, right, as I discussed with you, you can safely assume that Q1 will be cut off, and therefore, even whatever be the case, V out will be latched to VDD, because you do not have any current flowing through the system, and therefore, V out will be latched to VDD. As you start to increase your V in, you draw current from Q1, because this is the threshold voltage of the device. Till VTH1, the output will be latched to VB minus VTH2. What is VB? VB is this much. VTH2 is the threshold voltage of this device. So, remember your VGS minus VTH was the overdrive, right. So, this, if you look very carefully, this potential here will be nothing but VB minus VTH2, right. So, this is your this is your VGS2, right. So, if you look very carefully, Vx will be nothing but VB minus VGS2, but for the device to be on, VGS2 will be typically equals to VTH. So, VB minus VTH2 will be the value of Vx, and that is what you are getting here. Till a point, till what point? Till the point when the input voltage is just crosses the threshold voltage of the device. Which device? The common source device, which is the Q1 value. As it just crosses, the device switches on, and both the currents, and the current starts to flow through Q1 and Q2, because they are in series, and as it starts to flow, the voltage at output starts to fall, because V out will be referred to as VDD minus IDRD. Say there is a resistance also here available with you. So, with ID, so initially what was happening, ID was 0. So, you had what, this was 0, and therefore, V out was equals to VDD. Now, when the ID starts to flow, the V out starts to fall down, and that is what is falling down here, right. Similarly, your Vx will also, since your V out is falling, your Vx has to also fall, so that VDS between this and this of Q2, VDS of Q2 is almost constant, and therefore, you see it is almost the same drop is there between the two initially when a V in is relatively just larger than VTH1, right. I will just explain to you once again what I just now talked about it. What I talked about it is, initially when your V in is very low, less than threshold voltage of the device, Q1 is in the cutoff mode. When Q1 is cutoff mode, no current is flowing through this cascade structure. As a result, what will happen is your ID will be equals to 0, therefore, your V out will be latched to VDD standard case, and your Vx will be equals to VB minus VTH2, and we explained why it should be like that. It should be VB minus VGS2, but VGS2 equals to VTH2, because that is the on state of the device, and therefore, that is the overall voltage which you will get here. Now, as the input voltage crosses threshold voltage of the first device, the device gets on, current starts to flow, and when the current starts to flow through Q1, the same current flows through Q2, and therefore, the V out starts to fall down, right, and therefore, the V out starts to fall down. As I discussed with you just now, the V out starts to fall down. So, V out will fall down, as you can see, but as the V out falls down, you have to ensure that Q2 is in saturation, and therefore, Vx also starts to fall down, and the difference almost remains the same till few values of QH. As V in further goes on increasing, V in further goes on increasing, this value goes on still further increasing, right. As it goes on increasing, this is basically your gate and source, right, and this is always grounded. So, VGS is becoming very large, which primarily means that its overdrive is increasing, current is increasing. As the current increases, then it forces this voltage to further go down. So, that is the reason it is going down and down, right. Ensuring at one point of time, it might also happen that VDS of 1 might be even smaller than VGS of 1 minus VTH of 1, and forcing the Q1 to enter into triode region, fine. So, what I wanted to tell you from this whole idea is that by doing so, there is a problem here, that common source, if you remember, was very good amplifier, and common gate was a very good impedance matching purposes. So, cascode structure helps you to do both of them together, that helps you to match the impedances as well as gives you a improved gain with a much better gain available to you. So, if I draw the impedance diagram here, or if we draw the small signal diagram here, and the external load is RL, and let us suppose Q2 is the input current and Q1 is the driver cascaded current, then R01 and R02 are basically the resistances offered by those devices. If I assume this is Q2, if I this is Q1, and then I am giving a voltage here V in. So, if you look from this side, R in will obviously be equals to infinity, fine, and if you look from, therefore, if you look from this side, effectively value of R01 will be equals to R01. So, from this point, if you want to look inside, the effective resistance offered will be equals to R01. I think I need not explain to you why is it like that. Similarly, if you look from this side, right, and that is quite interesting, then R into resistance, input resistance of this one looking from the source side is 1 by GM2, right, plus RL by AV02. I will explain to you what do I mean by that. If you remember, the whole discussion was that even by inspection also you can predict the value of your input impedance. How do you do that? Just look from the source side, and from the source side, if the input impedance will be 1 by transconductance of the device. So, that is what is written here, 1 by GM2, and if you, why do you add this RL plus AV0? Because AV0 is basically the voltage gain, right. Now, so if you divide RL by the effective voltage gain, I get the input impedance at particular point, because RL is the external load resistance which you see, which you see here, right. AV02 which is the open circuit voltage gain of the second transistor, the common gate one, is given as 1 plus GM2 multiplied by R02, right. Now, of course, this could be approximately written as GM2 into R02. The reason being that GM2 into R02 is much larger than 1, and therefore, AV0 is equal to GM2 into R02. Why GM2 into R02? Very straightforward, GM-RD. So, where RD is the resistance offered by the device, GM is the transconductance of the device. Now, if you find out R out, and I am not deriving it here, it is out of scope, it will be given as R02 plus AV02 into R01, and if you find out, this will come out to be GM2 into R02, right, into R01, and this is nothing but AV into AV02 into R01, which I just found out here, right, A0 into R01. So, if you look very carefully on this profile here, what does it tell me? That the output impedance is raised by a factor of A0. So, if suppose you did not have any cascode, you did not have any cascode device, Q2 was not there, then I would have seen R01 parallel to RL. Now, since RL is very large as compared to R01, the output impedance would have been R01. Now, when you place a transistor Q2 cascaded over Q1, you actually increase the impedance by a factor of A0, where A0 is the open loop gain of my Q2. So, you multiply this with R01 to get the overall gain R out. So, cascade structures improves the gain by a factor of A0 into R01 and gives you a very large value of your output gain, right. So, this is a brief introduction or a structure of cascaded structures, right, and we will revisit this maybe at a later stage when we come back. Two things to take away from this discussion on cascaded, important for impedance matching as well as for high gain. The cost we pay for it is that now you have two transistors in cascade. Therefore, if you look at this very carefully, this will be V overlap Q2, and this will be V overlap Q1. So, the available headroom for me will be effectively equals to, if you look very carefully, will be VDD minus, right, V overlap Q2 plus V overlap Q1, right. So, this is the available headroom to you in the output side, which means that if you want the gain to be high for the cascaded structure, you end up having a reduced headroom. So, this is basically the headroom associated with this, right, which means that so this is connected to, so if you look very carefully if you look at the previous, this was connected to VDD, remember, connected to VDD, which means that it is VDD minus the sum of the overdrives which you see. While looking at this point, you please see that the while deriving this whole quantity, you please see that the base or the gate of Q2 has been grounded, right, whereas I am giving an input signal to Q1, right. Please find out why is it like that, why have we grounded Q2 and why we have taken out the signal through Q1 here in this case, right. This is to a larger extent explains the overall feature of cascoded structures using MOS devices. Let me come to the differential amplifier and let me see how can we change, because till now we were looking in the fact that we had a differential two differential output. So, I have a differential input and I had a differential output, and then what I was doing was I was subtracting V01 from V02 or vice versa, and this was del V out, right, and already I had del V in, and this was your overall gain which I saw. This was what we are doing till now. We also required to sometimes have a differential to single net conversion. So, this is the diagram for that you apply signals here VD1 by VID by 2. So, the difference divided by 2 plus and then difference divided by 2 minus, we already know what is VID. So, VID is basically V input 1 minus V input 2, let us suppose. So, it is basically this by 2 on this side, and then you apply V in 1 minus V in 2 by 2 with a negative sign on this side, perfectly differential signals, assuming this to be of infinitely high impedance. Then we find out the output impedance at this particular point V0, right, and it is straightforward way of saying that conversion of a high from differential to single ended input. As I discussed with you in the previous turn, what we were doing was that we need now to replace the RD, the drain resistance, by load, actual PMOS load. So, what people thought was that let us apply PMOS load in place of RD. The reason was PMOS is effectively giving you a larger resistance because of lower mobility of holes for the same dimensions of W by L. So, for the same aspect ratio, the resistance offered by PMOS will be 3 to 4 times larger as compared to NMOS of the same dimensions. So, if you look, this is exactly the same, this below side is exactly the same. If you look at the top here, RD is replaced by Q3 and Q4, right, and these are PMOSs. And quite interestingly, what we have done, one thing is that we have connected the gate of Q3 to the drain of Q3. So, now if you say V G Q3, right, is exactly equals to V D Q3, right. So, gate of Q3 and drain of Q3 are exactly the same, which is also equals to V gate of Q4, which means that now gate to source of Q3 and gate to source of Q4 is exactly the same. If I join these two, then it ensures that gate to source of Q3 and gate to source of Q4 are exactly same, which means that if I assume that Q3 and Q4 are perfectly symmetrical, their overdrives and the resistance will be also equal to each other. What happens when we join the drain to the gate side of it, right? When you join drain to gate, you ensure that the device is basically moving into a saturation mode and behaving like a resistor, right. If you short gate and drain, this is the reason. The reason being, remember what was the reason where VDS should be greater than equals to VGS minus VTH, right. Now, VDS is this much, VDS is this difference and VGS is this difference. Now, if these two are equal, then VDS is always equals to VGS. VDS drain to source will always be equals to VGS gate to source, agreed. So, drain to source will always be equals to gate to source because your gate and drain have been shorted with respect to each other, which ensures that which is quite interesting, that which means that this condition can never be applicable, which means that my device can never go into saturated region at all, right, but it will in the triode region behaving like a resistor. So, this can be replaced by a simple resistor. If you look back, since these are symmetrical, Q4 will also look like a resistor. This action is basically known as current mirroring. This is known as current mirroring, because this I will explain to you later on, maybe current mirror. The reason being that the current flowing through Q3 will be exact if the W by L ratios of Q3 and Q4 are same, the current flowing through Q3, suppose this is IQ3, will be exactly equals to IQ4 provided W by L of Q3 is exactly equals to W by L of Q3 is exactly equals to W by L of Q4. The same current will flow. Why? Because remember current is depending on VGS minus VTH whole square, right. It also depends upon the value of VDS. If you find out in the triode region, if you try and find out, it depends on the value of VDS, it is VGS minus VTH multiplied by VDS. So, if I am able to ensure overdrive to be equal and VDS to be equal, everything else taken care of, my current will be also equal, right. So, if you look very closely, this the difference between this point and this point will also be equal to difference between this point and this point, and therefore VDS will be also equal, my overdrive will be equal, and therefore they will behave like exactly symmetrical structures. With this knowledge, let me say we have this structure available here. So, as I discussed with you, I have a current source I, it divides into I by 2 here, I by 2 here. So, this is I by 2 here. Since this is I by 2, as I discussed with you, you will obviously have I by 2 flowing here, because it is a current mirroring action here. As a result, the current flowing through this will be approximately equals to 0, because all I by 2 has to be routed through Q2. So, the net current flowing here will be 0, that is what is written here, and therefore, V out will be equals to VDD minus VGS3. Why? VDD, this voltage, minus gate to source, source to gate, this to this. So, if you subtract this voltage, or even if you subtract this voltage, I get the voltage available at this particular point, pure Kirchhoff's law, and as a result you will see this. This is for the case when both your Q1 and Q2 are either shorted or having equal DC bias. Let us come to this point, you will have differential voltage given. So, I will have I, so this is minus VD by 2, and this is plus VD by 2, all current will be routed here. So, this is the current flow here. So, the other current flowing is here. So, net current flow was I plus I 2I, and therefore, V out will be having 2I available to you, right. So, this is what you get from this active load. Now, therefore, if you look here, which what I have done here is I have broken the Q3, Q4, Q1 and Q2 with their effective transient resistance, where R01 is the drain to source resistance of Q1, R02 is the drain to source resistance of Q2, so on and so forth, and I have sort of grounded. So, 0 volt is given to the input side, to the source side, right. So, I will assume that since it is 0 grounded, any voltage above them, the threshold voltage of the device given to the gate side will switch on the device, right, switch on the device. Now, this is R03 and this is R04 and so on and so forth. So, if you look from this side towards this side, the effective resistance offered will be R03 is parallel to Q3, and Q3, as I discussed with you, if you look from the drain and source side, the amount of is given by this is the resistance offered. So, this resistance is in parallel to R03, and that is what I have written here. So, this is replaced by this quantity, right. Whereas, if you look very carefully on this one, this is basically again Q4 is basically a VCCS, a voltage controlled current source, and therefore, GM4 multiplied by VG3 is the value, and R4 is therefore the resistance offered between the two. Assuming that this is a perfect current source, I am assuming that there will be no current flowing through R04 as such, right. So, what I see is I have a G, so if VID by 2 is the voltage given to the left arm and right arm, I can safely write down GM2 into VID by 2 as the current flowing here, and GM by VID2 opposite direction current will be flowing here, right, and this is what we get. Now, let me come to the mathematics of it. So, if you look very carefully, VG3 and this will require some amount of flipping of the PowerPoint presentation, VG3 is minus GM times VID2 into this whole quantity. What is VG3? VG3 is, let me rub this to make it clear, VG3 is nothing but the voltage at the gate of third transistor, right, is nothing but GM1 into VID by 2. Why it is GM1 into VID by 2? See, GM1 is the transconductance of Q1 into VID2 is the current which the transistor will allow it to flow. So, the same current will flow to Q3. So, that is the Q3 current here, right, I am sorry, right. So, I get GM1 into VID by 2 is the current. This if you multiply with the impedance, that will give you the voltage. What is the impedance? Impedance is nothing but 1 by GM3 because of this one, and R03 this one as well as R01, because you see this and this, these 3 will be in parallel to each other. As a result, you will get GM1 into VID2 into 1 by GM3 in parallel to R03. Now R01 and R03 is much larger as compared to 1 by GM3. So what I can safely write down, GM1 by GM1 by much larger than GM3, sorry, this will be GM3, I think this will be GM3, so make a correction. So GM1 by GM3 into VID by 2, right. Now I0 is the output current, right. Output current is GM4, if you look very closely, GM4 into VG3. Why? The VG3 is the same voltage you are applying onto the 4th transistor Q4, right. So VG3 multiplied by GM4 is one component of the current, and another component of the current is coming from this transistor, GM2 multiplied by VID by 2. So one current component is coming from here, another is this one. This one is GM multiplied by VID by 2, and this one is basically your, sorry, this one is basically your GM4 into VGS by 3 with a negative sign, right. So if you do a small manipulation, I get I0 equals to GM1 into GM4 by GM3 into VID by 2 plus GM2 VID by 2, assuming that GM1 and GM2 is equal to GM and GM3 and GM4 are equal, I can say I0 is equal to GM times IV, right, and therefore capital GM is equal to IO by VID. What is IO? Is the output current, VID is the input differential voltage, and therefore I use a capital GM. Capital GM is therefore the effective transconductance for the differential pair, fine. So capital GM is the effective transconductance of the differential pair, whereas small gm is the transistor level transconductance, fine. So this is the difference between the two. Let us look at the input and output resistance of the differential pair. If you look, input resistance will be given as 1 by GM1. We have already looked into the fact that input resistance given by here is GM1. R02 will be 2 times R02. The reason being that if you look from this side, you have R01 coming from here, one resistance is coming from here, and another one is basically coming from here. So they are equal, and therefore I assume it to be true. And therefore R0, the effective resistance seen at this particular point, these two are in parallel, and therefore I get R02 parallel to R03, right. We will explain to you this why R02 is actually equals to 2 R02, because R02, which is looking from this side, you will have 2 times R02, right, and looking from this side you will have these two in parallel, and that is what you get here, and therefore the differential gain will be nothing but GM's times R02 multiplied by R04. Assuming R02 equals to R04 equals to R0, I can safely write down AD to be equals to 1 by 2 GM R0, fine, because they are in parallel, right. So this is what you get parallel. Now we will look into common mode gain and differential gain. So common mode gain, if you remember what we did, we inserted VICM as the input mode voltage, and I replaced my current source by RSS. RSS is of the very large value of your resistance is being offered here. It is quite a large value of resistance, because output impedance of the current source will be typically very high. And then what we do a half circuit realization, and we divide it into 2 parts, and we give VCM here, and then since these are in parallel, so 1 by 2 RSS plus 1 by 2 RSS will give you RSS, and that is the reason we divide it into 2 parts, and we just separate it out, right, for calculation purposes. Similarly, when we look into the overall transconductance features here, so this is basically one of the half circuits. This is one of the basically the half circuits. So if you look at the half circuit, it is Q1 with 2 RSS here and R01 as the drain to source resistance offered by this thing, and therefore looking from the source side is 1 by GM1 is the effective resistance offered by the device, right. So what we have done is that we have just broken it up into half circuit and explained to you this basic idea. So let me come to you and explain to you each one of them individually. So I0 will be equals to V, so I0 will be the output current is VICM. Why it is VICM? VICM is basically this VICM, this divided by twice RSS, because twice RSS is the resistance offered by it, whereas GM, therefore GMCM will be 1 by 2 RSS, right, because current is equals to G into, so if you remember current will be equals to therefore voltage into G is the transconductance, and therefore I can safely write down G to be equals to 1 by 2 RSS. R02 is given by this formula. R02 is the R02 is basically the resistance at this particular point at Q2. This is R02. Looking from this side, this is the value of R02, right. R02, if you look at 2 RSS, why 2 RSS? Because you will always have 2 RSS here, right. You will have R02, the resistance, plus GM2 R02 into 2 RSS. What is this quantity? GM2 into R02 into 2 RSS into 2 RSS will give you the overall resistance offered by the device, right. Similarly, R01 by symmetricity you will get this. Similarly, if you multiply, therefore R01 and R02 are known to you, you can predict the value of I4 and VG3, and from here I will get common mode signal value to be equal to ACM to be equals to this much. Please do it yourself, these internal, I am not doing it in the lecture module, but please solve these yourselves to get these values, and you will get R04 by 2 RSS by 1. So, if you want your ACM to be really small, right, keep your RSS infinitely large, and that is the reason why we require almost an ideal current source here to make my RSS as large as possible, right. That makes my VCM ACM very small, and therefore my CMRR will be also very large. So, let me recapitulate what we did today in this thing. The CMRR of MOSFET is a strong function of output resistance, we have seen that, and therefore we have to ensure that it is a constant current source or an ideal current source. How can you increase the CMRR? By increasing the RO value, that we have also seen in the previous discussion. If you use a cascaded current mirror, your CMRR will increase because your ACM will decrease and your AD will increase. We discussed that point today also, that the differential voltage gain will be much higher in a cascaded current mirror design. Then the single ended active loaded MOS differential amplifier has a low common mode gain and correspondingly high CMRR, and the differential transmission of signal on the chip also minimizes substitute corruption with noise interference. This is quite interesting, the last one, which tells me that if you do have a chip in which you have got large impedances, R out is typically very large, it is actually a very good rejector of noise also. So, noise rejection capabilities of differential amplifier is typically very high. We have already discussed this point, but not only because of differential operation, but because also of high impedance nodes in those devices, right. So, with this we finish off this module, and from next module we will take up another subject, right. Thank you very much.